starting a new chapter, so first thing we've got pre-chapter questions, okay? And I have 3 questions today, so you're gonna make sure you put your name on the piece of paper, right? Give the answer to the 3 questions as best you can, then we'll swap off, we'll give a score on them, and then Colton will collect them in, okay? All right, so question number 1. So because we work under the action of gravity, right, what shape is the flight path of a long jumper? All right, so you got 2 options. If you can't remember the technical word for the shape of the flight path, I'm okay with the descriptive word that they use on that. All right, so preferably the technical name for the flight path. If not, can you come up with the descriptive? Okay. Because of the action of gravity, so because we're on Earth, if we did a long jump on the moon, we wouldn't see the same thing. All right, so because of gravity, what is the shape of the flight path of a long jump? It would be the same for a shot put or a javelin, right? If I throw something, what's the shape of the flight path? If I do a long jump as opposed to a vertical jump, what is the shape of the flight path because gravity is pulling on that object? It's looking good. All right. How many laws of motion are there? Question number 2. So Newton created some laws of motion that help us understand and explain what we're seeing. How many are there? Keep giving everybody else clues. All right, so question number 1, what's the shape of a flight path of an object because of gravity? Question number 2, how many laws of motion did Newton produce? Right. Question number 3, does increasing stability lead to increased or decreased mobility? Does increasing stability within a skill increase or decrease mobility in that skill?
You say that one time, please?
Sure. Does increasing stability within a skill increase or decrease mobility for that skill? All right, so question number 1, because of the action of gravity on an object, what's the shape of the flight path of a long jumper, or a javelin, or a shot put, or a basketball? Okay, what's the shape of the flight path? Question number 2, how many laws of motion did Newton come up with that we still use? How many laws of motion are there? Question number 3, does increasing stability within a skill increase or decrease the mobility within that skill? Need more time? Everybody okay? All right, so trade off. All right, so if you could, right? If they get it right, give them a 1, and total at the end out of 3 at the bottom of the slip, so that it's simple for me to see what they've got, and whether I need to check if they didn't get 3 out of 3. Do I need to go back and check how you've interpreted someone's answer? All right. All right. So action of gravity causes the flight path to be a parabola. You might have a semicircle, right? So the flight path of an object that's thrown, or the flight path of a long jumper, is a parabola. Semicircle is okay.
V-shape.
No.
What about arc?
Arc, I can take arc. I can take an arc. How many laws of motion are there? There's 3, yes.
What if you drew the shape?
Half a point.
If you do
3 laws of motion. Right, so answer number 2 is 3. And increasing stability decreases mobility. So answer number 3 is decreases. Alright, put a total out of 3, and Carlton will walk around and pick those up. Yes.
Boy, that's it.
All right, so coming around is a sheet that has a triangle, Newell's constraints. That's just for you for thinking about, working on, just a little worksheet for you to take home. Right, you should be able to fill in all the gaps, all the lines, and you should be able to tell what the arrow is representing. All right, so it's just a picture of Newell's model of constraints, just as a worksheet to help you when you're studying that. You should be able to fill that in. Okay? Remember that your first paper that you've got to write is going to be on this theory. So the better you understand the theory, the better the paper will be. Right? Alright, so we're going to start chapter 3, and there are a couple of articles on Blackboard for you to help with chapter 3. They're very practitioner articles, but they give you some ideas about how you can use the information from chapter 3 when you're coaching, or if you're in your PE gym, bless you, right? How do I actually take this concept and use it in every day, okay? And oftentimes, what I find with chapter 3 is it tends to be one that you can relate to quite easily, because it's using terms and talking about ideas that we use all the time when we're coaching. And so because a lot of you have had a lot of coaching, they're things that you'll hear people say. All right, so this chapter generally tends to be quite easy for you to follow. Okay. All right, so principles of motion and stability. Let's have a look here. Okay. Changes, developmental changes that we see in movement are predictable. So we said the other day that we have that kind of slight contradiction where we say that humans develop in a universal way. Okay, we can tell what's coming because we all do reasonably the same thing we're typically developing, but that we do it on an individual basis and an individual timeline. So there's a lot of variability and individuality in how those skills develop, right? But they're relatively predictable for a typical human being. So, and the changes that we see are really based on being able to fully optimize principles of biomechanics and physics within that skill set. Given an environment, given a particular task, how do we use those principles to create the most successful movement pattern that we can? Sometimes that's your brain doing its thing. If we go back to that information processing idea, that model, what's going on in that middle box, the processing, isn't always cognitive. Right? Your brain does a lot of calculation and makes a lot of decisions about things that you're not really aware of all the time. Okay. Sometimes it's very cognitive. Sometimes it's an absolute deliberate attempt to change a skill and utilize biomechanics to make a skill more effective. So it may be looking at height, it may be looking at distance, it may be trying to be as fast as possible. How do I use physics principles, biomechanics principles to create the best outcome that I want? So it's really important that we understand those principles as much as we can, which is why you also get a biomechanics class. Okay? What we're going to do in this chapter is just touch on real fundamental ideas that you can use to help explain some of the concepts we're talking about as we go through this semester, but we're not going to do an in-depth look at biomechanics. Okay. So developmental changes occur according to these principles, right? Our brain is trying to calibrate or recalibrate if it's something we're already doing to be as successful as possible within a set of constraints that are changing all the time, right? That's what we've already agreed on. That's the approach the book says, is that constraints, when they change, affect the movement pattern. Constraints are changing all the time. One day I'm happy, next day I'm mad as heck. Okay? I might lose some weight, I might gain some weight, I might grow. I was out walking this morning, it was below freezing, right? Hopefully another day it'll be nice and warm. Right? Constraints change all the time. Given the changing constraints, how am I going to optimize that movement? So sometimes, most of the time when we talk about biomechanical principles, we use a typical human, and we think about the typical developmental pattern. Try to keep in the back of your mind that if you're going to work with someone who's injured, and maybe they're rehabbing an injury, that then the challenges to that movement pattern change, right? The mechanics of the pattern will change because of the injury. So what am I going to see? How can I tweak something to get the most effective movement? What if they never rehab that injury fully and the movement pattern is permanently altered? How am I going to adapt things as I'm teaching them as best as possible given what we know about biomechanics? Or what if they're not typical, right? What if they're atypical? Okay, we looked at some swimming patterns last week of people with physical disabilities, right? The swimming patterns are mechanically very different from a typical person. Doesn't mean they can't be successful, because the person teaching them needs to understand mechanics well enough to be able to help them adapt their pattern to be successful, okay? And if you're working with people who are going through puberty, so if I'm working with teenagers, the brain experiments all the time with biomechanical principles, right? Because the constraints are changing so rapidly at that point in time, it's having to alter force production, and it might have to alter angle of release, all kinds of things depending upon how those constraints are changing. So you'll see a lot of variability in movement patterns at that point in time because the brain experiments. It doesn't know quite what to expect because all of a sudden the arm is 3 inches longer than it was when it learned the skill. Right? So what does it have to do to reproduce a successful skill pattern given this arm that's now much heavier and much longer? So let's take a quick look. Be thinking mechanically. What do I see when I look at this? Come on, don't take 5 hours to load. There we go. Right, so mechanically, what am I seeing? Right? She's not pushing very hard. I don't see a big deep knee bend.
No arms.
No arm swing at all, right? So if I was watching this, there's a lot of work to do to optimize biomechanical principles on this. Some of those principles we can help with now. Some we're going to have to wait until her constraints alter. Remember our idea of a rate limiter. Right? Are her legs strong enough to do a deep knee bend and push really hard? I would say right now, no. If I ask her to do a deep knee bend, she's likely just to sit down. Right? So that, but I might be able to get her to start to swing her arms a little bit, which would help. Right? So what changes here? What's different? Let's have a look. Okay. So we've got much different leg action here. Okay. She's bending her knees. Got a reasonable amount of force production. She's lifting off the floor quite a lot. We've got some arm swing. It's going in the wrong direction. Right? Mechanically, you can use a backwards arm swing for lift, but it looks as though the goal of this was to jump forwards. And a backwards arm swing isn't going to help you jump forwards. You're applying the force in the wrong direction. Right? So we've got some work to do on the concept of the arm swing because it's back to front right now. It's not helping her jump forwards. But we've got more distance, so we know she's applying more force if we were able to measure force application on the floor. So very different pattern going on there. All right. So hopefully the idea of the center of gravity is not a new one. Anybody never heard of center of gravity or center of mass? Yay! Good. All right, because we're going to play around with it a lot. All right, it has a big impact on what we're doing. So the point about which weight or mass can be said to act, it's purely fictitious, right? It's not a real thing. It's just mathematically, it's a lot easier if we consider the body to move around one point than if we have to consider the body as a whole, right? If we were doing a more advanced level of biomechanics, actually every segment of your body has its own center of gravity, right? So your humerus, a finger, part of your leg, they've all got their own center of mass or center of gravity. So it can become quite a complicated picture if I'm looking at how gravity is acting on every single part of my body. So we start off with a simplified version. Where does gravity act on the whole thing? Right? Doesn't have to necessarily be within your body. All right? We have some differences between males and females on the location. There's a slight difference. So men tend to be taller. They tend to carry a lot of their mass around their shoulders and their upper back. That raises their center of gravity a little bit. Women tend to be shorter. They tend to carry most of their weight around their hips and their thighs. That drops their center of gravity. So it's somewhere around the navel, but it's likely to be a little bit higher on a guy and a little bit lower on a girl, on average. Right? If you're Maria Sharapova, no, but for most of us, right? Doesn't have to be, though, within the body. Depending on what shape the body is making, that center of gravity may move outside the body. So in this very tight pike position, the center of gravity would actually be outside his trunk and in the fold there. Right? It would be in between the fold. So if I don't hike quite as tight, my center of gravity is going to be about here. Right? When we arch like this, it moves out the other way. So here, her center of gravity is somewhere out here. Right? So it will move out here. Okay? The key to understanding where it is that gravity, the force of gravity, always acts through the line of the center of mass, which is why we call it a center of gravity. Okay? Because that's an immediate reminder that that's where gravitational force is acting. So if I know where it is, I know how gravity is going to impact that skill. Right? Where's it going to be pulling on to change what the skill looks like? The only cause of movement for a human, if I'm looking at a human and they are moving, the only way you can move is to apply an external force. Gravity is an external force. So the only way to move is to apply an external force. That becomes quite interesting. Where's the force coming from? Linear motion, right? Or a linear force acts directly through the center of gravity. A rotational force acts outside the center of gravity. So, never remember to bring a ruler. I need a ruler for this. Anybody got a ruler? No? Okay. All right. See what we can do here. Okay, so here's my body, all right? And the center of mass is going to be somewhere around here. If I push through the center of gravity, what I see is linear motion. Whether I push horizontally or I push vertically, if that force passes through that center of gravity, motion is linear. Does that make sense? Right? However, given that my center of gravity is around there, if I apply a force outside the center of gravity, what happens? It tips. Rotation. Right? So, when I was coaching gymnastics, that's very nice to know. Because if I'm spotting a gymnast, where do I want to push her? Well, it depends on what the outcome of the skill is supposed to be, right? Am I trying to lift her up so she's in the air for longer? In which case I want to push as close to her center of gravity as I can as she's jumping, right? Or does she jump just fine, but she doesn't turn very well, and so what I want to do is help her rotate, in which case I need to apply force away from her center of gravity. So if I'm spotting someone in the gym, I've got to understand where their center of mass is, where their center of gravity is. If you're taking off on a triple jump, where's the center of gravity in relation to the force you're applying to the body? So it's really fun. Biomechanics is a heap of fun because it explains everything you're watching. So Newton's first law, right? Law number one, what have we got? An object at rest stays at rest, and an object in motion stays in motion unless it's acted upon by a force. Okay, so if I am standing still, I remain standing still unless a force is applied. So that could be someone tackling me, right? I'm going to move if I get hit by another player. It could be me applying a force that gets returned back that makes me move. Okay? Nothing moves unless I apply a force to it. And if it's in motion and I want to change its direction or I want to stop it, I have to apply a force. So once it's in the air, the flight path is fixed unless we apply another force to it. Okay? If it's moving and I want to stop it, there has to be a force applied to stop it. What happens if I throw a ball up in space? Okay? Just keeps going, going, because there's no gravity, there's no external force out there to stop it. Right? When we're on Earth, what goes up has to come down. But it only comes down because of gravity. Right? And because of the mass of the Earth, there's quite a strong gravitational pull. So we come back down to Earth. Right? Impacts everything you see when we're looking at movement. Because nothing would look like this if we didn't have gravity pulling on us. A couple of terms that are related here. Inertia is the term we use to represent the resistance to movement related to the mass. So the more mass an object has, the more resistance to move or stop that object has. Right? So if I've got my great big rugby player, I have to apply way more force to move him than if I've got my little gymnast. Why do we want defensive line? Defensive line? Football guys, help me out. Yes, those things, right? The great big guys. Why do we want them as big as we do?
Because you want them to move someone out of the way.
Yeah, we want them to be able to move someone out of the way, and we don't want anyone to be able to move them unless we want them to move. Right? So, the more inertia they have, the harder it is to move them or stop them once they're going. Right? So we want them to be able to hit someone and keep going and knock that person down. We don't want the other person to stand there and then bounce off. That doesn't do us any good, right? We've got to be able to keep going and push someone over. I want to make it very hard to stop them.
So if you chop them, you hit them below their center of gravity, so like their knee.
Right, so they have to tip. You don't want to hit them through their center of gravity. Where do you tackle? momentum, mass times velocity. So the amount of momentum I can create is a product of my mass times my velocity, which we tend to use speed. Technically it's not correct, but how fast am I going? How much mass do I have?
Hypothetics when freaks in nature like J1, 270-pound man that's as fast as like me. 20 pounds.
I suspect that that answer would be more physiological. I bet if we looked at the size of his bones, the weight of his bones, and the amount of fast twitch muscle fiber he has, he's a complete freak. Yeah, I don't know that particular individual because I'm not a football person, but yeah, it's,
Usain Bolt with that.
yes, yeah. If you look at anybody that is world class at a particular sport, they're not physiologically normal, period. Right? In order to be that good, you have to be freaky. That's okay, freaky's good, right? You guys are freaky, somewhat. Not quite freaky enough to be world class. Okay? But you are way different than a typical person physiologically. So when you come to XFIS and we talk about that, you'll see that that plays a big role. How much force I can produce, right, when we're looking at mechanics, is somewhat dependent, mostly dependent, on my physiology, which I don't get to control. I can train as hard as I can train, but I can't change physiology.
Is there a way using this you can find the limit of someone's ability?
Yeah. Yeah, you can. You can. Most of us, our limits are relatively. So, if we look at the first law then, we have to exert a force. That means we have to produce the force in the first place, which comes back to the physiology. How much force can I produce? How strong am I? How fast am I? Okay. I have to exert force to move an object. I have to exert force to move myself or to change my direction. So when you look at injuries, okay, if you take one of the athletic training classes, or if you're on the field and a teammate gets hurt, oftentimes we get hurt when we're trying to dodge and change direction. Okay, because the amount of force you have to apply to change direction may be more than the bone or the tendon or the ligament can tolerate. And so we get hurt. Right? In gymnastics, a lot of kids get hurt twisting because they're applying a lot of torque, a lot of force, and then they don't allow their feet to go, and so the knee joint can't tolerate that amount of force. More inertia, so remember, the bigger the mass, the more inertia someone or something has. More inertia means it's harder to move it, and therefore I have to apply more force to have the same outcome. So if I'm learning to swing a bat, right, one of the things the brain has to do is how do I apply, or how much do I have to apply? If I'm looking at force production, what do I have to do to overcome the inertia of the bat to make the bat swing? Okay? Most of the time we're not cognitively thinking that question through, but your brain is thinking that question through. Because your brain has not only your arm to move, now you've stuck this great big long heavy bat on the end of it, and you've changed the whole mechanics, because now the center of mass moves away from the body because of the bat, right? I've got to apply a lot more force to move that bat to try to hit a ball. That's point one. So that's the first thing I've got to do. When we work with younger children, one of the fun things is getting it moving is not so difficult. Learning to stop it once it's got moving becomes the real challenge, right? So when you give someone a tennis racket or a bat of some description and they're first playing around with it, quite often what you'll see is that, right? Because their brain can work out how to contract the muscles to create the force to get going, but now it doesn't know which muscles to contract to stop it once it's on the move, because it's a different set of muscles. Okay. So that can be harder, that's very challenging. It's one of the fun things about when I'm watching people learn to move, what on earth is going on in that brain? Right? What can I see mechanically or developmentally that helps me understand how the brain is learning that skill? Oftentimes, our goal in sport is to move an object further. So I want to throw further, or it's got to go faster. So if the object is me and I'm a 100-meter runner, how do I go faster? Right? Or if I'm a baseball pitcher, how do the distance, I don't need to throw the ball any further because the distance is the same, it's dictated, but I might want to go a lot faster. What do I have to do? Right? So given law number 1, I have to increase the force delivered to the object. I need to get stronger. Okay. Or I can increase the distance over which the force I have right now is applied. You could run into it, you could take a longer step into it. Okay. So what constraints, if we go back and we use our triangle here, what constraints might affect me applying more force or increasing the distance that I apply the force? So if I'm going to take a big long step, what do I have to be able to do? Balance. What does it take to balance? I've got to be really strong. Okay? Really strong. So there's no point in me telling someone over and over again, take a longer step, take a longer step. I told you 3 times already, take a longer step. If they've got really weak legs, they're not going to take a longer step, because I can't stand on 1 foot long enough to take a longer step. Right? So, you guys can find that piece of video and click on that, but I have linear distance. I can increase the linear distance that I apply the force. So I can increase the step length. So if you watch really good soccer players, right, the step before they strike the ball can be very, very long, because the longer that step is, the longer they've got to apply force. If you watch a baseball pitcher, sometimes that step is longer than they are tall, right? It's ridiculous. They're so supple. Got to have really good hip flexibility to take a really long step. I can increase rotational distance, so the rotary distance that I'm applying force can be greater if I increase my range of motion. So we sometimes get a little bit sloppy about doing our flexibility training, because it's not quite as fun as doing our weight training. Flexibility is a little more uncomfortable for most of us. Our perception is that it's more uncomfortable, right? So we tend to slack off a bit on the flexibility, but the bigger my range of motion, the more time I can apply force to the ball. Right, so we're looking for the optimal relationship between force and distance all the time. Sometimes an improved performance isn't just about increasing force. Sometimes increasing distance helps. All right, so law number 2. Law number 1, if it's at rest, it's staying at rest unless we apply a force to it. Law number 2, that the force an object can produce is related to its mass and its acceleration. Okay, F equals ma. And the acceleration, therefore, I can do a very simple piece of math jiggery-pokery. If F equals ma, then A equals force divided by mass. Right? So I can look at acceleration, because oftentimes in sport in particular, acceleration is a key. So if I'm trying to throw a shot put, how is that different to trying to throw a basketball? Okay, so a shot put has much more mass. So I would have to apply a lot more force. That's logical. If I can't apply a lot more force, then the shot put isn't going very far. If it's at constant velocity then, so acceleration is the change in velocity over the change in time. Well, how does my speed, my velocity, change over a period of time? From point A to point B, if my speed changes, I accelerated. Or I negatively accelerated, I decelerated. Right? So I could be getting faster or slower. If I'm at constant velocity, then what does A equal? Okay. So if, let's do it visually because it's easier visually. Right? If A equals the change in velocity over the change in time. If velocity is constant, if I'm on the treadmill and the treadmill is set at 6 miles an hour, there's no change in velocity. So this would be 0. Doesn't matter what this is. What does A equal? 0. So A is always 0 if I'm at constant velocity. Sometimes that makes life a lot easier because that's one thing I can take out of the equation. So second law, let's think about the second law. At any given time, if I'm looking at strength as a constraint, on a given day, in a given PE class or a given training session, someone doesn't get stronger, right? Getting stronger takes time. So on any given day, an individual can only throw as hard as they can throw on that day. Everybody agree with that? Right? Assuming 100% motivation and effort, right? So we're not looking at motivation and effort. We're just looking at physically. I can only throw as hard as I can throw on a given day, yes? Okay. So, if I have a peak force capability on that day, right? If I've got a constant amount of force, it doesn't change. This is as much force as I can produce. How do I increase acceleration when we're throwing a ball. So I'm doing a lesson plan on throwing, or I'm working with a summer camp for an athletic team, and we've got people who are beginners or less experienced, right? And we want to increase acceleration because that often produces a better outcome and makes the skill more fun, right? Because the faster, if I can increase acceleration, the ball's going to go further. It's going to hit the target harder. It's more likely to knock the bowling pins over, whatever it is I'm doing, right? So, if I've got right, A, we said acceleration is force over mass. So on a particular day, I'm working with an individual and they're not succeeding, right? I've said, you've got to throw the ball and hit that target. And it isn't getting there because the ball's not accelerating enough through the air. This isn't going to change. So, exactly. So, let's say my force is 10 newtons, and the mass of the ball I gave them was 5 something, right? Then we've got an acceleration of 2 meters per second squared. That's the right unit. Right. And the ball falls short of the target, over and over and over and over and over. Is that fun? Is that person going to be motivated to keep practicing that skill? Right. Is their movement pattern going to improve if they don't practice? No. Right. So I have to do something. And the only thing I can do, because I can't change this on the day, I can change this over time if we put them on a strength program. Okay? Change the mass of the ball. Shivaji said, that's good. I have to have options of the equipment that I give them. I can't just have one type of ball. Change the mass of the ball. Now I have much more acceleration, and bingo, the ball hits the target, and they're like, woo!
Yeah.
Got it! Right? Oh, let me try that again. Now I can start to impact the movement pattern, because now they want to practice. Right? And all it took was applying a very simple biomechanical principle and changing out the ball and giving them some acceleration. Okay? I have to be flexible. I have to understand. And you want to know why it worked. Right? To me, that's the key. If I want to be a really good coach, or I want to be a really good movement teacher, PE teacher, or some other kind of movement, if I'm going to teach a Zumba class, why did changing that thing work? Because I can just haphazardly pick things out of the air. And let's just see what happens if I do this. Okay, well, at least you're being flexible enough to change things up and try something different. But if you don't know why it worked or why it didn't work, how are you going to keep repeating? Like, how are you going to keep being successful? The really cool thing about movement that no one gives us credit for is we are some of the strongest scientists out there. Everybody says biology is a science, chemistry is a science, physics is a science, PE isn't a science, PE is just playing games. Wrong. Wrong. Right? Don't ever let them tell you you are not a scientist. Everything we do is based in science. Okay? All right, so So, we will look at the